Now, sometimes when you're balancing equations, it's convenient to use fraction. Well, you end up with a fraction instead when you actually have a balanced equation. Here you've got 2 carbons here, and you've got 2 carbons here. The thing about the oxygen is that because of this odd number here, you've got 3 here, and you've got 4 here, for a total of 7. Okay, and so because this is 2 here, it's 7 divided by 2 would balance this equation. But this is never the final endpoint. When your balance is achieved, all the coefficients have to be whole numbers, okay? So any fractional numbers here have to be converted to an integer. And that's done simply enough by multiplying everything through here by 2. So instead of a 1 here, you have a 2 here. So it's C2H6, that's ethane, right? This right here was a glitch on the slide. This is supposed to be a subscript. This is not a, supposed to be a large number. You end 7 times 7 halves ends up with 7 here. 2 times 3 gives you 6 here. 2 times 2 gives you 4 there. So there's additional information that we include in our chemical equations. If something is in a gas state, such as the hydrogen here, you put it as a gas. If something is in a liquid state, such as water here, you write that as liquid. If something is dissolved in the liquid, it's aqueous. So salts in a liquid are AQ, right? And then if something is a solid, it's an S after it. So this helps keep track of the reaction as well, and provides the specific information of the state at which each of the molecules is in. Special conditions necessary for the reaction are sometimes designated by writing a word or a symbol above or below the equation. For example, the delta, okay, over the arrow means that heat is added to the reaction to go from the reactants to the products. Okay, sometimes something is put inside there as a catalyst as well, and so you write out the name of, or the letter designation of that particular compound. And so, but that's the special conditions for in which either catalyst or heat are added to an equation. So stepwise balancing procedure. How do you go about balancing an equation? Okay. The first step is to write down exactly what the equation is. Then what you do is you do an inventory about how many you have on each side. You've got 1 calcium ion here. You've got 1 calcium ion here. You've got 2, because this is a subscript outside of this. That means everything in here is taken by 2. 2 times H, that means you have 2 hydrogens on this side. And that you also only have 1 hydrogen on this side. You've got 2 carbons here, plus another carbon here, right? So that's 3 carbons. You've got 1 carbon here, and you've got 1 carbon here for 2. So those aren't balanced either. You've got 6 oxygen here. 2 times 3 gives you 6 here. And you've got 3 more here. So that's a total of 9. Here you've got 3 plus 3. So that's 6. You got 2 sodium here. Yeah, 1 sodium here. And we've already taken into account these. So that's what we have on each side, okay? Now, when you've got something like this right here and this right here, these ions need to be kept as ions going from each side of the equation. So you'll keep this, you have 2 of these present here. You've got 1 of these present here. You've got 1 of these present here and 1 of these present here, okay? So keep those as units, but your overall totals still have to include them. So placing a coefficient of 2 in front of the NaHCO3 will balance the equation. Oops. So if you put that here, you'll then have 2 on each side here. you'll have 2 of these, you'll have then 2 of these here, 1 here, and 1 there, right? So the inventory then gives you the following ones in terms of all of the ions. The coefficient ratios are 1 to 1 on the reactant side, going to 2 to 1 on the other side. Okay, so you have to have a 2. There should have been a 2 right here, right? Okay, so that's the only change that you. I'm sorry. Yeah, there has to be a 2 right here for this to be balanced. Okay, so the coefficient ratio 1 to 1 going to 2 to 1 will balance the equation. And again, I apologize for that mistake being there. They do not allow me to correct these or change these slides. The generalizing equations. The combustion reaction is the following. Anytime you have a hydrocarbon, in other words, a carbon plus hydrogen or carbon plus plus hydrogen plus some other elements, that plus oxygen with a little delta here is going to be burned to form carbon dioxide and water. So in a hot air balloon, you have C3H8O2, and so this is not a balanced equation, is it? Because you've got 3 here. So you'd have to have about 3 here, okay? You would have 4 here, 4 times 2. So that means you'd have, with 3 here, you would have 6, plus 4 there, and that would be a total of 10. So you'd have to have a coefficient of 5 in front of this one right here. And so this is when, and this is the formula for propane. Propane is burned to generate heat for a hot air balloon. Now there's other ways of classifying reactions. The last one was a combustion reaction. Anything burned is a combustion reaction. Any organic plus oxygen going to carbon dioxide and water is a combustion reaction. A combination reaction is when you have 2 reactants forming one product. Okay, so you can see that's a combination. Decomposition is you have 1 reactant and it breaks up into 2 separate products. Replacement, you have X, Y plus Z, and so Z replaces the Y, and then Y is all by itself over here on the product side. And this is where the negative ion is being replaced. XY plus A going to AY plus X, the positive part is being replaced. And these right here are types of redox reactions, and we'll talk more about those later on. Ion exchange reactions are ion of one compound interact with ions of another compound. And you can have a solid precipitate forming, you can have gas forming, or water forming, right? So we'll talk about more of each one of those next. So the oxidation reaction. Oxidation is a loss of electrons. A reduction is a gain of electrons. So here you have Fe2O3. Oxygen is a -2. So you have 3 of those, so this is a -6. So for this to work out right here, that means each iron here has to be a +3. So the iron is going from a +3 oxidation state to a 0. Solids and have 0 for their oxidation state. So it's going from +3 and it's getting 3 electrons to make it an oxidation state of 0. Carbon starts off at a solid state, so this starts off at 0, but right here you've got 2 oxygens here. Each of these is a -2, right? And so this means the carbon here is a +4. So the iron ore is gaining electrons, the reducing agent in this reaction. Okay. So this is gaining electrons. This right here is losing electrons. And so that is being oxidized. That is the oxidizing agent. So some redox reactions involve the transfer of electrons from a reactant species to yield a given ionic product. Again, this would have a 0. Each of these would be a -1. So that this right here would still be a -1, but this right here would become a +1. It's helpful to split the overall reactions in individual equations called half reactions. So this right here is +2 electrons, gives you 2 Cl minuses here. 2 of these with a 0 gives you 2 pluses, 2 electrons. So the sodium atom loses electrons, the chlorine atom gains electrons. For the redox reactions of this sort, oxidation is the loss of electrons, reduction is the gain of electrons. Therefore, sodium is being oxidized, chlorine is being reduced. Okay? It's important to understand the distinction between, and it's always in terms of loss or gain of electrons. Loss of electrons is oxidation. Reduction is a gain of electrons. So, the sodium functions as a reducing agent, okay, because it provides electrons for the chlorine. Chlorine functions as an oxidizing agent because it effectively removes oxygen, it removes electrons from sodium. So just going back here, sodium is oxidized, chlorine is reduced. It's oxidized, but it serves as a reducing agent. This is reduced, but it serves as an oxidizing agent. So what the agency is the opposite of what actually happens to this material. So some redox reactions do not involve the transfer of electrons. This one right here, it forms a covalent bond, so it's a shared bond. It's not an ionic bond. Okay. So the product of this reaction is a covalent compound, so the transfer of electrons in the explicit sense is not involved. The oxidation number or oxidation state of an element in a compound is the charge of its atoms would possess if the compound was ionic. So even though this is a covalently bonded compound, you think of the chlorine as something that has a -1 and the H is something that has a +1. Just like for those earlier examples when I mentioned oxygen would have a -2, and then from that you determine what the electronic charge or the oxidation number would be for the other ones. So the rules for assigning oxidation numbers. The oxidation number of an atom in an elemental substance is 0. Okay? Elemental substance or solid, right? A solid, elemental state, just an elemental state. The oxidation number of a monatomic ion is equal to the ion's charge. In other words, if you have sodium, it would be +1. So the oxidation number for common nonmetals is usually assigned as follows. Hydrogen is +1 when it's combined with nonmetals, -1 when it's combined with metals. Okay? And you know what are, from the periodic table, which ones are metals and nonmetals. Oxygen is -2 in most compounds. Sometimes if it's -1, very, very rarely it's -1/2. Usually for the ones I will be giving you, think of it always as -1. And halogens are -1 for F always, and usually it's -1 except when combined with oxygen or other halogens. It may have something else in those cases. And number 4, the sum of the oxidation numbers for all atoms in a molecule or polyatomic ion equals the charge on the molecule or ion. And we'll stop that because that ends the oxidation assignments.